Now, I did change some equations here, but the idea is that when I connect them when I connect the capacitors like this in the final state, they're in parallel to each other. Initially though, we initially though at the very beginning, when we've just connected the capacitors with the opposite plates, our charges at that point in time add up to 420 microcoulombs, okay, at that point in time, and they will in the final state as well add up to 420 microcoulombs. But for the voltages, they're going to actually change at the very end. But initially, in the very beginning, the voltages are indeed 35 volts each, but they're going to sort of redistribute until we actually have no charge in any of these capacitors. Now we know that the total charge is equal to the total equivalent capacitance times the total voltage. We can rearrange for total voltage. And I know that the equivalent charge is this much, and there's the equivalent here, down here. So initially the voltage on each of these guys is 35 volts. The charges initially on each of these guys are, like we calculated, 105 microcoulombs on this guy. And if I just focus on this plate, it is actually negative 105 microcoulombs. If I focus on this plate, this is for the second capacitor. So we calculated the charge here of the second capacitor, which is 315 microcoulombs. And in this case, it's positive 315 because I'm looking at the positive plate, microcoulombs. Now what I'll do is I'll add these charges up. Of these two plates to find Q equivalent. Q equivalent in the initially, when we've just connected these capacitors in parallel after having removed the battery, is going to be negative 105 microcoulombs plus 315 microcoulombs. We're just adding Q1 with Q2, but Q1 happens to be negative, that's all. So this Q equivalent is equivalent to 210 microcoulombs, and that's positive. Okay, so keep this in mind now. Now, when these guys are in parallel, their equivalent capacitance is still the same, because before they were still in parallel. So we're still using 12 microfarads for the equivalent capacitance. It's just that the voltage now across both of these guys is going to change. It's going to equal to 35 in total. So like voltage from the first capacitor and the voltage of the second capacitor will add up to 35 volts. But it's not going to be like 35 volts each. So now when we come back to this equation, we just calculated, we accounted for, what we did initially here is we found the charges on each of these capacitors separately, and initially, when these capacitors get connected after removing the battery with opposite plates, the charges are still the same as the charges we found here. Right now, we've basically just connected all these guys in this way, and we haven't allowed any current to start flowing yet. we haven't allowed these capacitors to start discharging yet. We've sort of stopped time initially when we've just connected them in this specific way. So at this point right now, the charges are still the same as they were in that initial state on each of the capacitors. I hope you guys understood that. So yeah, again, down here on this plate it would be positive 105 microcoulombs, negative 315 microcoulombs, the same thing. So what we did now is we added these two charges to find the equivalent charge in this final state, which happened to be 210 microcoulombs, and we know that the capacitance, because they're still connected in parallel, the two capacitors, is 12 microfarad. So we can find the voltage on each of these capacitors, which is going to be the same, by plugging these values in. So the micro cancels with the micro and we get 17.5 volts. So forget the total voltage here, this is actually wrong. It would just be voltage on any one capacitor. That's what this voltage would mean in the formula. So the voltage on any one capacitor can be found this way, by taking into account the charges and the new equivalent capacitance that is still the same in this question. So we get 17.5 volts, and this is the voltage on the first capacitor, the new voltage on the first capacitor, and the new voltage on the second capacitor, and they both add up to 35 volts, so that's good. We have still preserved the total voltage. And is that correct? Yes, 17.5 volts each. That's awesome. So we got these guys correct. Now we have to sort of find the final charges on each of these capacitors, and this is how we're going to do it. We already know the voltage, the new voltage now in the very final state of each of the capacitors, so we're just going to use Q is equal to CV for each of the capacitors separately. So charge on the first capacitor is equal to C1 V1, which means C1 is 3 microfarads. V1, as we found here, the new V1 is 17.5 volts. And so the new charge on the first capacitor, after having removed the battery and having connected them and having allowed some time to pass, is 3 times 17.5, which is going to be 52.5 microcoulombs. So is that correct? I'll check. So Q1, yeah, it was 52.5 microcoulombs. Awesome. That's correct. Q2 is equal to C2 V2. Again, C2 was 9 microfarads. The voltage is the same here, so 17.5, the new voltage. 0.5 volts. And this is equal to 17.5 times 9, which is 157.5 microcoulombs. Now let me check if that's the correct answer for the charge of the second capacitor. Yes, it is. It's 157.5. So there we go. We've sort of solved the question, and I'll try to now summarize it for you because I do believe I may be a little bit disorganized. You see, you notice how the charges don't actually add up to 420 microcoulombs? Yeah, so in that scenario I was wrong. I had said that the charge is always conserved and that the charge in the initial and the final state would be the same. The total charge, the total charge would be the same in the initial and final state. That statement itself is wrong in this question, so please ignore that. I was just trying to explain, I was trying to test if I was right or wrong, but I'm wrong. Now, to kind of summarize the question for you, I'll erase stuff first. I'll like erase everything first. In this question, and for these types of questions, it depends on what they're asking you for. But generally, at least for this question, what we did was first we wanted to find the charges in the initial state. We wanted to find the charges on each of the capacitors. To do that, we needed their capacitances, which we already had, but also their voltages, which we also already had, realizing that these guys are in parallel. So that's the first step we start off with. I know that in the previous part 1 video, I kind of did a few steps that are not really useful. I found the equivalent charge, which was useless. You don't have to do that. Again, it's 10 p.m. right now and I'm kind of sleepy. That's why. So yeah, it's very simple. With this question, you start with that. You know you have C1 and C2 and V1 and V2, especially because these guys are in parallel. So you solve for their individual charges, find those individual charges, and you're set. You're good to go. The next thing you do is you connect these guys, you switch the plates, and you kind of write down the charges this way. And then what you do is you sort of use Q equivalent that equation and add up these charges like this. So this plate with this plate and this plate with this plate. You only need to do it once though for any pair of plates. And then you get whatever that answer was. Okay, so then you have the equivalent charge, and this is the initial equivalent charge. Initially, when you've just connected the circuit, but no current has flown yet, or no capacitors have discharged yet. And initially, yeah, the voltage would be that. But we want to try to find the final voltage on each of the capacitors. The final voltage on each of the capacitors is going to be the same. Why? Because these guys are in parallel. So final voltage in the first capacitor is equal to the final voltage in the second capacitor. We realize that. So we use this equation. Q equivalent is equal to C equivalent V. This V represents the voltage on any one of these capacitors, the final voltage on any of one of these capacitors. 1 or 2. Doesn't matter. So you rearrange for VF, and we did the following. We took that Q equivalent we got and divided it by the new equivalent capacitance. In this case, there was no new equivalent capacitance because these guys are still connected in parallel. And so then we kind of got the voltage, and we know the voltage was the same. And then once we had the voltage on each of these capacitors, we go back to solving the new charge for each of these capacitors. And that's pretty much the gist of this question specifically. I hope this helps, and again, watch my videos on 2x speed. Have a good day.